Hello and welcome to another video. In this video we're going to be working on count submatrices with top left element and sum less than k. And so in this problem you're given a grid and integer k, and you want to return the number of submatrices that contain the top left element of the grid and have a sum less than or equal to k. So they show you these examples where these are like the ones you could build, so pretty straightforward. But let's take a look at a custom one. So also notice that the constraints are 1,000 each, meaning you have to have like an n squared solution, and by n squared, since it's already a matrix, it's kind of more like O of n solution where you're traversing each item in the matrix roughly at one time. Maybe like you can have an n squared log n as well. And so the way to figure out these sums, like the way to figure out submatrices with a sum, is almost always a prefix sum. So let's kind of walk through how this would work with a prefix sum and like what matrix that would represent. So for each row, we're just going to build a prefix sum of the row. So this will be like 1, 3, 6, 10, 15. And then we have 5, 6, 8, 11, 15, 4, 9, 12, 13, 15, 3, 4, 6, 10, 15, and finally last one, 2, 3, 7, 10, 15. Okay, so this basically represents a prefix sum of the row, right? So like, obviously a submatrix like this would be fine, but the problem with just having a prefix sum of the row is what we really want is a prefix sum of the matrix. So ideally for like this cell, this is the prefix sum of the matrix. And the way to do this is for every row, not only do you need the prefix sum of the row, but you also need to add the column above it because that would represent the matrix. So for example, here, if I add the column above it, that would represent this matrix. Here, if I add this column, that would represent this matrix. Here, I need to add all of this. And so I can just kind of like do a prefix sum down as well. So let's show you what that would look like. So the first row is fine. Now for the second row, we're going to have to replace some stuff. So it'll be 5 plus 1. So this will be 6. Whoops. This will be 6. Now this will be 10. So 10, 13. 13 and 15. So we're basically doing a prefix sum down on every column now as well, which is still O of n, right? So 3, we add like we're doing the prefix sum down, so we add 6 to 3, so we get 9. 9 plus 9, 18. 18 plus 4, 22. Yeah, and then we get plus 3 is 25. And let's kind of just like make sure we're on the right track. So this 25 should represent this whole matrix. So let's see, so this is 3 plus 6, 9 plus 9, 18, 25. Yes, that's correct. So we're doing the right thing. So let's continue. So here we have 6 plus 8 is 14. So this is 26, 32, and 39. And then 2 more columns. So hopefully this makes sense. Like you do the prefix sum for the row, and then you want to do the prefix sum for the column as well, because that will actually represent, like that will make this corner the sum of this whole matrix. And there are tougher problems where you're not including this, so you have to do a bunch of subtractions. Like if you wanted the prefix sum of like this matrix, the way you would do that is you would get the prefix sum of this matrix subtracting a couple things. So it's a little bit trickier, but this one is like the easiest one. Okay, so 10 plus 11 is 21. Then 21 plus 13 is 34. And then 44 and 54. And then we'll talk about an optimization as well that I made that I think for bigger inputs will make a difference, but for this one didn't make too much of a difference. So here, this one's pretty easy. So it's all just 15. So it's going to be like 15, 30, 45, and so on. So 15, 30, 45, 60, 75. So now that we have this, we can literally just look at every number less than 30. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or less than or equal to 30. Yeah. So we have 10 here so far, 11, 12, 13, 14, 15, 16, 17. So we have 17 submatrices. So for like any number less than 30, like this, that would mean that this matrix is less than or equal to 30. So that's why the prefix sum is really easy. You just build it and then you do that. But there is an optimization here, and I'll talk about it and I'll look at it in the code. So first of all, notice that every single row, like when we're adding, only depends on the row above. So you can technically just only store one row instead of storing this whole. You can also override the grid, but that's not like the best practice. So because like this row, the sum of this row depends on like this row, and like it depends on this whole row, right? And the row above, because we're just adding the previous row. You can technically just do this row by row. So you can calculate this row, and then you can just make a new row here, get the prefix sum there, and then add the total for the previous row. So instead of storing this whole thing, you can only store 2 rows, which would give you, instead of n by n space, it would give you n space now, right? So it's kind of like a DP optimization. Another optimization you can make is you can actually, as you build these rows, you don't have to keep building them like too far. So for example, let's say we're building this row and we calculate this 34. Well, we know anything past this is not going to work either, right? Because we're looking for 30. So as we build this row, as soon as we get a number that's bigger than k, we can just stop. So we can just build a row like this, and then we can, like, as we're building the row and we get the numbers, we can just what's it called? Modify the result as we're building it. So for this row, we can just have this because we don't need anything past it. And additionally, as we're building like the row below, we can look at the row above, and we only need to build the row below up until the same like distance as the row above. Because if this value was too big, then obviously you keep adding, right? So this value is going to be too big as well. So that's why you don't have to keep building the rows fully. As soon as your row is too big, you just stop and you just go to the next row. And that way you can save a lot, depending on your numbers. Like instead of building this whole matrix, you might have to build like half of it or a third of it or so on. So let's take a look at the code. So here's the code. So you get the rows and the columns. I think it actually might be n by n, so you probably don't even need the columns. Let me double check. Oh, no, it's not n by. Yeah, it's not n by n, so you do need the rows and the columns. But essentially, yeah. So you initialize the first row to just be zeros because I'm gonna have a recursive thing that's gonna build a row and then take the row above it and add numbers. So I just wanted to initialize a row to be zeros. So then when I'm building this row, I can just add a bunch of zeros. And essentially for every single row, you make a current value, which is just going to be the if I didn't want to do this like whole build this way and then build down, you can just do it all you can do that all in one operation, because you just keep track of like what's my current row total for the row I'm building, right? So you'd say like, okay, I have 5 here, 6, 8, 11, 15. And then my value in this cell is going to be my current row total plus the value of the row above. So you have a current row total for the row you're building, and then you just keep adding like the current cell you're on, and then you check, is my actual prefix sum of my cell less than or equal to k? If it is, let's actually use it. And in mine, I modified this current row in place. So like I would calculate this value. We can do like one iteration of that, I guess, just to show that pretty clearly. So let's go back. Okay. So for like this row, it's pretty straightforward how to build it. But the next row, instead of actually building a row, I would just do it in place. So this is going to represent this row over here. So we basically take the grid value. First of all, like I said, we have a running total of the sum of the row. So in this case, it's just going to be 5 for the first cell. And then we take the value above. So the value above is 1. So then we can say 5 plus 1 is 6. So now this is going to be 6. Then same thing here for this cell. This is going to be this value 1. So we add that to our running total. So we have 6 plus the row above, which is 3. So this is 9. And that's correct, right? Because it represents this. And then the next cell, the value, so this was 6. The next cell, the value is 2. So we get 8 plus the row above, which is this one over here. So this is 14. Then we add 3. So we get 11, yeah, plus the row above, which is 10, so we have 21 now. So 21. And finally, we had 4, so we have 15 plus 15, so we have 30. So you can see how you can modify this in place, and as you're modifying it in place, just like check the value, calculate, and if it's less than 30 or less than or equal to 30, modify your result. So this would be the sum of the previous, like this would be the sum of this cell here. So it's 6, 9, 14, 21, 30. And if we take a look at like this cell, or let's say this cell, for example, this represents this matrix like this. And this matrix would have 10, 16, 20. Did I do that right? I don't think so. No, it's 21. Yeah, it's 21. Okay, so this would be 21, which is that. So you can do it in place. You can build the whole prefix sum on whatever you prefer. I just prefer to save a little bit of space. And then, like I said, as you're building your row, if your element becomes too big, you can just stop building the row because everything to the right of that will also be too big. That's basically what I did here. I just said, okay, if my row is too big, because I was doing it in place, like let's say I override this value. Let's say I'm trying to override this value. And I'm trying to override this value, and I get like 45. Well, what I basically do is I just say like, okay, well, I don't need this value, so I just take this as my row now, and now I'm only going to override these values. Because anything below this value will be bigger than 45, because you're just adding and adding and adding. So this kind of like is a pretty good optimization, I think, where we're only using one row, and we're shrinking our row when our numbers get too big, because we don't need to fill out the whole thing. Yeah, and then we can run this. And as far as runtimes, I think there might be like a better implementation, but I think if the constraints were a bit tougher, this would be better. Obviously, it's still going to be like, it's still going to be n squared. It's just going to save space in practice. So yeah. So this is going to be time m by n, not n squared, I guess. M by n by m, whatever. And space will just be the space of a row now. So this will be like, if it's m by n, it'll be like this. You can optimize it more, like if you want to. So another one I can see is I'm building it with a row, but instead you can build it using a column. Would that work? Yeah, I think it would. Yeah, and then in that case, if your columns variable is smaller than your rows, you'd save like a little bit more space. So instead of O of m, it would be like minimum of m and n, which would also work. But yeah, felt like it was like going a little bit too far. So, but yeah, it's gonna be all for this one. Hopefully you liked it. Pretty simple one. It was pretty straightforward prefix sum. And if you do have any questions or if I screwed up anything, just let me know in the comments. And please like the video and subscribe to the channel if this was helpful. And I'll see you in the next one. Thanks for watching.